Hello everyone. Today is the 55th day of Leetcode 75 challenge. Let's begin with the 55th question. Question 162. Find peak element. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given an integer array nums of length L. Fine. Array of length n. A peak element is defined as an element that is strictly greater than its neighbor. Basically, if we have 4 here, it is a peak element if in the left hand side it has an element which is strictly less than 4, suppose 3 and suppose here 2. So this becomes the peak element. The elements outside the bounds of the array, for example nums of -1 or nums of n. Basically after this, if this is the outer part, nums of -1 and this is nums of n, are considered to be minus infinity, meaning that boundary elements have only one neighbor to compare with. If basically they are trying to say that if this is the array and this is the boundary elements, this is the outside bound element, suppose this is -1 and this is n, this is considered as minus infinity. And if we have any element here, so this element has only one neighbor to compare with, which is this. Okay, so this will be compared with left hand side and the right hand side value. That's all. Okay, this is what they are trying to say. Your task is to return any index I such that nums of I is a peak element, and you must implement a solution that runs in log and time complexity. The question specifically points out that the time complexity should be of log n. Let's see why. Now let's look at the constraints before. Nums length is from 1 to 1000. The value of the nums could be from negative to the 2 to the power 31 to 2 to the power 31 minus 1. Okay, and nums of I will never be equals to nums of I plus 1 for all valid I. Fine. So I hope you understood the problem explanation. Let's move to the next slide. Now let's understand the input output explanation. So let's take the first example, which is 1, 2, 3, and 1. Okay, and indexes 0, 1, 2, and 3. So here, if you could see, if you take this 3 value or the value in the index 2, it is greater than 2 also, and it is greater than 1 also, which basically means this particular number is greater than both of its neighbor. Therefore, the output is 2, the index 2 basically. Okay. Now in example 2, if you could see 1, 2, 1, 3, 5, 6, and 4, right? Here you could see that we could write 2 also because 2 is greater than both of their elements, both of its neighbors elements, or you could write 6, which is also greater than its neighbor elements. The indexes will be 0, 1, 2, 3, 4, 5, and 6. Okay, so here the output is 5, but we could also return index 1 also because it is also a true case. So I hope you understood the input output explanation. Let's move to the next slide. Before going to the further slides, let's understand what is binary search or the concept of binary search. Fine. A binary search is an efficient algorithm that finds a target element or optimal value by repeatedly halving the search space. While commonly used on sorted arrays, it also applies to monotonic functions. Monotonic functions basically means, I will explain that. Okay, let me explain what is binary search. Binary search is basically, if this is a range, right? This is a range. So you keep on doing half of it. Suppose you started here, okay, in the middle, and then you will make the range half. Okay, then you have this particular range with you, then you again started in the middle, then you again make the range half, right? So this way the binary search goes. Okay, I will explain in more depth. So you could see here it comes in monotonic functions, biotonic function sequences, and decision based problems with a clear true false boundary. So monotonic functions means increasing or decreasing, which basically means you have a sorted array in clearly increasing or strictly increasing manner. Fine. Or decreasing means that the number is strictly decreasing, 5, 4, 3, 2, 1, whatever, right? So that is a monotonic function. uh, that is a range in which you will use the binary search in a monotonic function. Okay, then comes the biotonic sequences. Biotonic sequences are basically the first it goes on increasing manner, then it goes on decreasing manner, and then it goes on increasing manner, right? Or it goes in vice versa way. It comes in decreasing, then it goes in increasing, this way. These are the sequences I have given you. Okay, and decision based problems with clear true false boundaries basically just it's way like you have a range and you got a value. Is it equals to the number which we are going to find or not? Then in that case we use this decision based problem. This is just a format of the sequence which you get, in which you can clearly figure out whether you have to use binary search or not. Okay, so it works wherever the solution space has a predictable pattern, enabling us to eliminate half of its at each step. Okay, it has to be a predictable pattern, right? Since monotonic stack is a predictable pattern, bitonic is a predictable pattern, right? So though it that's the way it goes. Okay, now how binary search works, fine, that's the important thing. Suppose let's take a range. Okay, uh, 1 2 3 4 5 6. Okay, and start with the entire sorted array. So this is a sorted array, right? Now how it work? We calculate the midpoint. How to calculate the midpoint? 0 1 2 3 4 5, right? So what is the low value here? So we have two variables in binary search. One is low and one is high. Okay, and another is mid. Now low takes the uh, index value from the starting, and high takes the index value from the backside, and mid is the calculated value for the particular range mid index. Okay, so low is basically here 0 and high is right now is 5, right? And if we calculate this, how much it going to be? 5 divided by 2, you get 2, right? Okay, you get 2. So this is the mid value right now. Okay, so what happens? You got 2, right? So you come to index 2 here. What is the value of 2? It's 3. Fine, wait. Now thing is, we compare the mid with the target. Suppose basically we use binary search to find a target value. Okay, so the target value, suppose here is 4. Okay, but you are standing at 3, right? Because you got the mid value as 2. If you could see, if it is equal to the target found, if the target is less than the array of mid is mid is the index value, right? And here array of mid, which is array of 0 to array of 2, is the value is 3, correct? And but we were searching for 4 value. The target was to be 4. Okay, now you could see that okay, the target value is greater than the mid value. Okay, so what you will do, you will search the right half. Now you will understand what is the repetitively halving the range. Now what will happen? Your low, so low value will come here. Okay, since high was standing here itself, because this is not the range you need, right? 3 is not required in your search space, because 3, because the value which we are finding is greater than this particular value, right? So we'll make the range here, right? So what will happen? Now low value is what? Low value is 3, high value is 5 right now, and mid value is 2, right? So now what happens? Now you will calculate this mid value again, right? 3 plus 5 gives us what? 8, right? 8 divided by 2 gives us 4. So the mid value for this range is this, right? You come here, 5. Now you will check that okay, this 5 is greater than the mid value, the target value, right? This array of mid is greater than this target value. Now what we'll do? We will go for the search the left half of the range, whatever you have, right? So what happens in that case? Since low was standing here and mid was here and high was in the end, right? Because this space is done, right? We don't require this space anymore, and anything beyond this space is not required also, right? So what will happen? Now L value is 3, right? So 3 plus 4 gives me what? Divided by 2 gives me 7 by 2 gives me 3, right? We get 3. So what will happen? The high will come here and it will stand here. Okay, and mid value is 3, correct? Now what happens? You check. Okay, you will see that okay, the mid value is 4 and the target value is also 4. Therefore we found the target. So we then return this particular index, or we return true or false as per the question, right? So we repeat until the target is found or search interval is empty. If the search space says that, you might not have the target, right? And if uh, h comes here and l comes here, because basically they cross each other, that means that the value is not present in the search space. Okay, so I hope you understood that how binary search works. Now binary search basically works on sorted array, ascending or descending, or bitonic arrays, as I said, or monotonic functions, right? So these are the ways where binary search happens. You have to look for a pattern there. Okay, and why it's efficient? It's efficient because the best case is O of 1 if the middle element is the target, and average worst case is log n. Each step halves the search space. So whenever you do a half of any search space, suppose this is the search space, right? And if you iterate, it will take O of n time complexity. But if you make it a half, you came here and you make it a half, and again you make it a half. So this is a time. This is basically a mathematical calculation. When we do something, and any step, if you make the particular thing in half, 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 like a merge sort, time complexity comes out to be log n, right? So that is why it is much more efficient than any other iteration. And search complexity usually takes O one time complexity, and if you are doing a binary search space, then it takes log n recursion stack. That's all. Now this binary search is basically efficient for fast lookup in sorted data, optimizing problems with monotonic pattern, reducing the brute force time from O of n to log n. Okay. Now, where binary search is used. Binary search is basically used in sorted arrays, basic direct applications like binary search question number. This I've just given you the references of the questions also and where it is used. Right, this is what this particular PPT is. This slide is all about. So, like first and last occurrence, if you have to find the first and last index of target, right? They find the first and last position of element in the sorted array. These are the questions where you need it. You could go and practice these questions if you want, like search insert positions. If target not found, return the positions where it would be inserted. Example, search insert position. Basically, you have to insert 7, right? And you got a value 5. You got a value 6, and then 8, right? So 7 will be inserted here, right? So this could be done using binary search. Finding pink element in an array. Peak element comes in the biatonic, monotonic, biatonic sequence as I explained earlier, increasing and decreasing, right? So this is will be a peak element, right? Then you have to find the condition why it is a peak element, because the left hand values are lesser and the right hand values are greater than this particular element. Now rotated arrays are also there. Rotated arrays also work as a biatonic sequence. Suppose you had 4 here, 1, 2, 3, right? So it was a rotated array this way. Modified binary search to handle rotated version. This is question number. You could go and check in Leetcode 33. Cocoa eating bananas or minimum eating speed. This is the most common and most important question to understand binary search on answer or binary search on answer space, not the array. Answer space is basically you have to figure out by yourself that what could be the range of binary search rather than depending upon the array. Okay, like you have to assume that the search space will be n or it would be 6 or whatever depending upon the answer. Fine. So I hope you understood the binary search concepts. Let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. So let's do that by understanding the goal first. So we are given an array nums of integers where each element has its own two most neighbors. Okay, a peak element is defined as an element that is strictly greater than its neighbor. This is clear to us. If this is 4, that its neighbors would be 2 and 3. Okay, or less than that. We are allowed to assume that nums of -1 and nums of n is infinity. That is, the elements outside the array are always smaller. This is also clear, because if there is an element, to this to check whether this is a peak element, we will have to compare with its right element here, and this left element, which is basically out of bound, is taken as negative. Fine. Our task is to find the index of any one peak element. So there could be multiple peak elements. So what could be the brute force? A brute force approach would be to linearly check all elements, compare with neighbors. This gives O of n time, but is not optimal. Okay. So why? Because if you go for a O of n solution, I to j, then it will take time complexity of O of n, because you're iterating the complete array. Fine. And this is a brute force solution, but it can also be explained to the interviewer. But since the question specifically says us that it should be completed in log of n time complexity, this directly points to only one and only concept, which is binary search. Okay, if a question specifically says you that you have to complete it the problem in log n time, please go and think about binary search solution always. Okay, if you have to reduce any time complexity from O of n to log n, it's binary search. Okay, simple as that. That is what I have written here. The constraint demands a more efficient solution with log n time, suggesting a binary search approach. Okay, so I hope you understood the goal. Let's move to the next slide. Now let's try to visualize the process. Okay, So I have already created an array for your understanding so that we could visualize the process. So we know that we have to use binary search. Okay. And how binary search work, we also have the knowledge of that. So let's do the dry run here. Okay. If I take the mid value for this particular scenario, it will be 6 plus 0, 6 divided by 2, which gives me 3, right? Index 3. So if you go to the index 3, we have value 3. Now, what a person will do, or what the question says? Question says that check its neighbor. Simple as that. So what we will do? We will check that if mid minus 1 is less than the mid value, and also if mid plus 1 is also less than the mid value. Okay. If both of them are less than the mid value, we will return that value, right? But here in this case, we could see that it is not, because 3 is greater than the mid minus 1 value, but it is smaller than the mid plus 1 value. So what we can do? We know that we can assume that if we go to the left hand side, this particular thing will result in much more smaller values. We are assuming that. Okay. Second case, we know that mid plus 1 is greater than 3, which means if somehow we come and stand at mid plus 1 value, which is index 4, therefore there is a 100% chance that mid minus 1 will be always smaller than the mid plus 1 value. Is that making sense to you? Which means that if we forget about this particular search space and go to this particular search space, then there is a chance that if we fall on this value 5, then mid minus 1 or the index minus 1 will always be less than the particular index in which we are standing, which is basically 4, right? So that is why what we will do in that kind of scenario, what we're going to do is that our condition will be, or I will write it here. So the first condition will be if I will just write, okay, mid, I will write the index here. If mid is greater than mid minus 1 and mid is less than mid plus 1, in that case I said that we'll throw this search space, right? Which means that L equals to mid plus 1, correct? Now let's try again. Now what we can do is that now the our search space is from here to here, right? So 4 plus 6 is 10, so it will be 5. So if we come and stand at 5, we got value 6. Then what we're going to do, we're going to check that if mid is greater than mid minus 1 and if mid is greater than mid plus 1, what we do, we just return the index which is mid, correct? So in that scenario, here you could see that this is the mid value and this mid value is greater than 5, and it is also greater than 4, which is basically means mid plus 1 and mid minus 1. So in that case we will return the mid. So we have figured out two cases here, and the third case would be, I will write it somewhere here, that if mid, I could write that here instead. If mid is less than mid minus 1 but mid is greater than mid plus 1, what we will do in that case, right? Suppose if there is a case scenario that this is 3, let it be 4, um, let it be 6, okay, and let it be 2, and let this be 9. So if by any chance if you're standing here, it says that mid is less than mid minus 1, which is true, but it is greater than mid plus 1, right? So in that case, what we will do? We will do h equals to mid minus 1. Let me write it clearly. So in that case, it will become h equals to mid minus 1, right? Which means that we will reduce our search space from this, and we will forget about this particular search space. So if you fall in this value, it is greater than its left hand side and right hand side. So this will be our output. So using this idea, we can perform binary search by comparing the middle element with its neighbors. And this guarantees we shrink the search space in half in every step, leading to a logarithmic solution. So I hope you understood the visualization process. It was pretty straightforward and simple. Now let's see how we can simulate this. Fine. First and foremost, we have to handle our edge cases. Okay. If the array has only one element, okay, if array has only one element, we will return 0, because if this is an array having 2, we know that this is minus infinity, this is minus infinity, and index value for this is 0, right? So in that case, we will return 0. This is the first edge case. And second edge case is that if suppose num of 0 is greater than num of 1. Now suppose num of 0 is here, suppose 6, and here it is 2, and here we know it is minus infinity. Okay, so if num of 0, which is this, if this is greater than nums of 1, right, 6 is greater than 2, true, therefore we will return 0. Why? Because it is because the anything after 0 index, which is minus 1, minus 2, minus 3, which is out of bound, is always negative infinity, right? That is why this 0th index value will always be greater than this particular value. And since index 1 value is also smaller than index 0 value, therefore we'll return 0 in that case. Similarly, for the last index also, if num of n minus 1, if this is greater than nums of n minus 2, basically if it is 8 and this is 6 and this is infinity, and nums of n minus 1, which is this, is greater than n minus 2, which is this one, 6 value, will return n minus 1 as the output, right? Because this element will be always greater. So I hope you understood this particular 3 edge cases, which are very crucial here. Let me clear this up. So after handling the edge cases, we will start our binary search, or we'll put the pointers equals to l equals to 1 and r equals to n minus 2. Reason being, we already have checked the edge cases in the index 0 and at index n minus 1. Okay. Now, while l is less than r or equals to r, this is the simple binary case template. We compute the middle index. How to compute the middle index in Python? We will write mid equals to l plus r minus l divided by 2, right? In Leetcode, we have to write in this format for our for taking out the mid value, because sometimes it results in out of bound or memory issues. Okay, if the value is too much big. If nums of mid is greater than both its neighbor, we found a peak element, we return the mid. This is the first edge case, which basically means that if mid is greater than mid plus 1 and mid minus 1. Okay, if the right neighbor is greater than nums of mid, we move right. Basically means if mid is this and mid value is less than mid minus 1, mid plus 1, and mid minus 1 is, if this is the condition, what we do, we go to mid plus 1, right? Otherwise we are at mid minus 1. Okay, if no peak element is found in the loop, we return the index 0, though by constants we should always find the 1. Okay, this is the how we gonna simulate this particular problem. Let's move to the next slide. Now what we figured out, we figured out that a peak is always guaranteed to exist due to the negative infinity assumptions on the boundary. Rather than scanning all the elements, we can leverage the slope property, because slope property is basically this biotonic sequence in binary search. There is a monotonic sequence which keeps on going this way, and this is the biotonic sequence. This is monotonic, always increasing or always decreasing. Fine. So here in this particular scenario, we had the biotonic sequence, and this allows us to apply binary search, shrinking the search space efficiently. So I hope you understood the intuition explanation. Let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're gonna solve it. Let's start by handling the edge cases, which we already discussed. Okay. First, check if array has only one element. Return true. The element is the peak, or return 0 index. Right. We basically we should return 0. So it will be like if n equals to 1, return 0. Okay. Second is if the element if the first element is greater than the second element. This is the condition. We return 0 index again. Similarly, check if the last element is greater than the second last. If n minus 1 is greater than n minus 2, we return n minus 1. Why we are doing this? Because peak elements can appear at the boundaries due to the assumption that out of bound values are minus infinity. Okay. Now at step 2, we initialize the binary search. We set two pointers L equals to 1, R equals to n minus 2. Because we already handled the edge cases, so now we can do binary search in the middle section. Okay. Now at the step 3, we perform the binary search. It is a simple template of a binary search. While L is less than equals to R, we repeat the following steps. We calculate the mid value in this way. Check if the current element is greater than both the neighbors. If nums of mid is greater than mid minus 1 and nums of mid is greater than mid plus 1, when this means that we got the peak element, so we will return true, or we will return mid as it is a peak element. If the right neighbor is greater, we move to the right side by setting L equals to mid plus 1. This means that the slope is increasing, so the peak must be on the right hand side. You could take it as this way. Suppose this is a mountain or the biotonic sequence, increasing, decreasing. And if you're standing here, and when you check that, okay, this element is smaller, but this element is greater, this means that slope is increasing. And somewhere or the other, there would be a peak. What you do? You move here and you stand here. Got the point? And similarly, this case could be if you're standing here and this is a decreasing element, but this is an increasing element. So what you do? You do h equals to mid minus 1, so you come back. That is what written here. Else, left neighbor is greater or equal. Move left by setting r equals to mid minus 1. This means the slope is decreasing, so peak must be on the left. Now the step 4 would be return a fallback index. Basically, after writing the complete edge cases, written, then while loop, which is basically the binary search, is also written. After completing all of this, we return 0 for the main function, which is basically a fallback. Why we do this? This line is a safe fallback, though the logic guarantees a peak would be found in the loop. It is guaranteed that there is a peak, but for our making a safe code to be written, we write a fallback which is return 0. Okay. So I hope you understood the approach explanation. Let's move to the next slide. The code is the exact copy of the approach we discussed. Let's understand it line by line. First thing, taking the length of the nums array given to us, checking for the base cases or the edge cases. If n is 1, return 0 index. If 0 index is greater than the first index value, return 0 again. Similarly, the last index value is greater than the last second index value, return the last index value. Yeah, I know it sounds confusing, but this is a very simple thing. Yeah, and L equals to 1, R equals to n minus 2, because we have already searched the 0th index and n minus 1 index. So we'll go for the remaining one. This is the complete binary search. This is the first condition. If it's a peak element, return mid. If it is not a peak element, the slope is increasing. That means we are going this way. Then L equals to mid plus 1. The slope is decreasing. We have to go backward. Therefore, mid minus 1. And this is the fallback I talked about. Return 0. Okay. So the time complexity for this particular code becomes log n now. This log n is the time complexity for the binary search, purely binary search. So there is nothing to be explained since we're dividing the problem into half and half all the time. That's why the time complexity reduces to log n. Okay. And the space complexity is O of 1 because we are not using any kind of data structure to store our solution. So I hope you understood the code explanation. Let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. Let's take this example. Okay. 1, 2. So I have brought down the code here for much more clear understanding, and also I have written the example here. Let's start the dry run. So first n equals to length of the nums, which is basically here 7. N equals to 7 here. Okay. If n equals to 1, here n is not equals to 1, so this will be skipped. If nums of 0 is greater than nums of 1, is nums of 0 greater than nums of 1? Let it be L and please be H. Okay. No, it is not, right? Skip. Is nums of minus n minus 1, which is this, is greater than n minus 2? No, it is not, right? So what we will do? We will skip that part. Now we will initialize our left and right pointer for the binary search. Okay. While L is less than R, we take out the mid. Mid for 1 plus 5 is 6, right? So it will be 3. So our mid is standing here. I will let m. If mid, nums of mid value is 3, right? Is 3 greater than mid minus 1? And also is it greater than mid plus 1? No, it is not, right? So this condition false, get false. So we come to the elif. Is nums of mid greater than mid minus 1? Yes, it is. 3 is greater than 1, right? You could see that here. And nums of mid is less than mid plus 1. Yes, it is not greater, it is less than 5, correct? So what we do, L equals to mid plus 1. So L comes here. Now we go back again. Again we calculate the mid, which is 4 plus R is what? 5 minus 4 divided by 2 gives us 4 plus 0, which is 4, right? So mid will come and stand here. So again we will check for the condition, is 5 greater than 3 and greater than 6? No. So this condition gets falsified again. Now the second condition, yeah, 5 is greater than mid minus 1, but it is less than mid plus 1. So what will happen? L equals to mid plus 1. So L will come here. Now we'll calculate the mid again. 5 plus 5 minus 5 divided by 2 gives me 5. Okay. So the midpoint is 5 now. We will check, is mid greater than mid minus 1? Yes. Is mid greater than mid plus 1? Yes. So return mid, which is index 5, right? So we return 5 from here, and that is our output. And the binary search terminates here and returns 0. This is a fallback. So our try run is complete. If you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, and the code, and also the code of binary search or concept of it if you don't know. After that, do a dry run by yourself on 2-3 examples, and I'm pretty sure you will understand both the solution and the thought process behind it. Let's move to the next slide. Now, since we are familiar with the problem and the solution, let's move to the lead code and code the solution. We'll take the length of the nums first. And if n equals to 1, we return 0. If nums of 0 is greater than nums of 1, we return 0. If nums of n minus 1 is greater than nums of n minus 2, we return n minus 1. Okay, these are the edge cases. Now L equals to 1, R equals to n minus 2, right? While L is less than R, less than equals to R, we calculate the mid, L plus R minus L2. If nums of mid, okay, nums of mid is greater than nums of mid minus 1, and nums of mid is greater than nums of mid plus 1, that means it is a peak element, so return the mid index. L if nums of mid is greater than nums of mid minus 1, but nums of mid is less than nums of mid plus 1, we return, or we don't return. What we do? We do L equals to mid plus 1. Okay, we go to the increasing slope. Else H equals to mid minus 1. Okay, after that we write a fallback, which is return 0. Let's try submitting for the sample test cases. Okay, now let's finally submit the solution. So we have successfully submitted our solution. Now, code of the problem is available in my GitHub repository. You can find the link in the description. Thank you, everyone.